Hello everyone and welcome back. We're now in 8.3. We're talking about a confidence interval for the mean. Now back in chapter 7 we talked about the mean twice. First when we had the population standard deviation, then we could use a z-test, and again when we only had the sample standard deviation, in which case we had to do a t-test. In chapter 8 we're skipping straight to the better assumption that we do not have the population standard deviation. So we still have a standard deviation, but it's the sample standard deviation. So again, we're going to be talking about a t-test. We're going to be using t as our critical value. So we're going to start just by looking at an example of how we would state the confidence interval for a mean. So looking at that first question, we're looking at the random variable and the parameter. Of course, x is the random variable, and mu, remember mu is it's the true mean of the random variable in the population. The assumptions, we're not making any distinction here about z and t. We're going straight to the case where we only know the sample standard deviation. So there's only two assumptions here if you compare that back to chapter 7 where we had 3. So the first, exactly what you'd expect, a random sample of size n is taken. And the second, one of two cases, or maybe even 3, the population is known to be normally distributed. So we might be told that it's normally distributed, or we might actually have to do some of the tests we learned to show that it's normally distributed. Or that's not the only way that we know that, or we have something that's normally distributed. The sample size can be over 30. So that's probably exactly what you were expecting. Now the confidence interval here is also probably exactly what you were expecting. That is, it's the point estimator, in this case x bar, and minus the margin of error, that's the capital E. That contains the population mean, mu, and then the upper bound is x bar, that is the point estimate from the sample, plus the margin of error. The margin of error here, notice, has a t in it. That's t sub c. That's the bridge between the level of confidence and the confidence interval, because of course E makes the width of that confidence interval. There's an S there, and notice that that S is the sample standard deviation. And S is being divided by the square root of the sample size n. So E, our margin of error, is that determines the width of the confidence interval because it's what we're adding and subtracting to the point estimate, in this case for means, x bar, to trap, that is to contain, the true population proportion, mu. Now, x bar is, of course, the point estimator for the population parameter, the population mean, mu. S is, and this is important, this is why we're using t, S is the sample standard deviation. Remember sigma, the Greek letter sigma, is the population standard deviation. So when you see S, you've got the sample standard deviation. N is our sample size, so no great surprise there. And E is called the margin of error. That's the thing that we're adding and subtracting to x bar to get that interval that contains the true population mean, C% of the time. Now, T sub C is our critical value. T sub C is a t-score, and it's a t-score because we do not know the population standard deviation. It's the critical value, and remember that it's the critical value where we get C from taking the complement of alpha. So that's also a bridge between a hypothesis test and a confidence interval. C, our confidence level, is the complement of alpha. So the statistical interpretation, so we say something along the lines that there is a C% chance that the interval, we show it exactly the way we did before, that point statistic x bar, and it is being added and subtracted to with E. So we're subtracting E to get the left endpoint and we're adding e to get the right endpoint, and that is containing or capturing or is the endpoints for an interval that contains that population mean mu. Now the real-world interpretation is when we say this as close to a useful way as possible. We remember our units. So we say, what that interval is and what the units are for it. In your homework, you're going to find some questions that ask you for the critical value t sub c. So we're going to go through that as a separate question, but remember, the goal here really is to find a confidence interval for a population mean when the population standard deviation is not known. But we're going to start just by finding some critical values, t sub c's. So in the past, even when I was taking this course as a student, we had tables for this, and we actually found the number closest to the area, the probability that we were interested in, and then we figured out what values of t were closest to that. We're going to use the Gossett Student T Distribution Calculator from Chapter 6 to find our critical t values. Recall that the degrees of freedom is 1 less than the sample size, and we're going to find the area inside, that is, around the mean. That'll give us our boundaries, negative t and t, and of course our critical t value is the positive one. So let's look at this first example. It says find the critical value when the confidence level is 90% for a sample of 350. So let's go into the applications for Chapter 6, where our Student T Distribution Calculator is, and put in the information. So the mean is 0, the standard deviation is 1, the degrees of freedom is 1 less, so that's 1 less than 350, so that's 349. We're interested in finding the boundaries, and that is inside, and it looks like we're interested in a confidence level of 90%. And when we do that, we learn that the critical t value is 1.6493. So when we enter that, 1.649 looks like a good approximation for t sub 0.9. Let's get a confidence interval. The way we do that is we have to start with the sample mean and the sample standard deviation S. That sample standard deviation will then become the standard deviation of the sample means when we divide by the square root of our sample size n. That will give us our confidence interval by using the Gossett Student T Distribution Calculator. And again, the degrees of freedom is 1 less than the sample size. We're interested in the inside area. So let's look at an example here. Use the Gossett Student T Distribution Calculator to find the confidence interval when the confidence level is 95% for a random sample of 29. So let's put this in. So the 29 tells us that our degrees of freedom is 28. And our confidence level is 95%. It then says that the mean is 56 and the sample standard deviation is 8.6. So let's put in the mean of 56 and let's calculate this inside 8.6. Then we're going to make this into the standard deviation of the sample means by dividing by the square root, SQRT, of the sample size n29. It does that for us. We could have gone off to the side and done it as well, and we have our confidence interval 52 point, it looks like 73 rounded to 59.27, and we should also say that's with 95% confidence. And the last thing we're going to look at is an even easier way of doing that, and that is also in GeoGebra in the probability view by doing a t-estimate of a mean. So if we go back to our class resources and go down to the Chapter 8 applications, we have a statistics view already. We can change this to a t-estimate of a mean. So notice that we're now talking about the sample, the confidence level 95%, the sample size 29. So let's change that. The mean is 56. And the sample standard deviation was 8.6, so let's enter that as well. This gives us our lower limit and upper limit. It also gives us the interval as the point estimate, which was, of course, our sample mean, plus or minus the error. Okay, so let's look at an example, and we return to 20 IQ scores of famous people. It says a random sample of 20 IQ scores of famous people was taken, information from the website of IQ of famous people, and then using a random number generator, so I'm thinking this was a simple random sample, to pick 20 of them. Find a 98% confidence interval for the IQ of a famous person. And so the first thing we do is we say what the random variable here is. So X is the IQ of a famous person. We're interested in the population mean. That is the average IQ of all famous people. So we want to use a sample to make a claim about the population. So we've got 20 of these X's, of these random variables. That's our sample. And we're going to use that relatively small amount of information, assume it really was randomly selected to do this. So one of the first things we have to remind ourselves is this was a simple random sample. She used a random number generator to choose 20 of these famous people at random. Now, we do need to talk about the standard deviation, and if you reread the question, it never says anything about the standard deviation. So you might say, well, maybe we need to run one of those 3 tests we've got to show that the data is normally distributed. Or maybe we should simply say we don't know that the data is normally distributed, and maybe the test is unreliable. But just like height and blood pressure and cholesterol level, the IQ scores are normally distributed. So we can say that that is one of the sets of data that we know are normally distributed. So you may be expecting us to use a spreadsheet in GeoGebra, and that's exactly right. So let's go into the applications for Chapter 8, and that second one already has the data for the IQs of 20 randomly selected famous people. So we can click on that. We can then launch a GeoGebra spreadsheet to get that analytics. Let's go into View, turn on Spreadsheet, turn off Graphics and Algebra, and let's paste in that data. So let's select that column and do one variable analysis. Let's see the statistics. We click on Statistics and go down to a t-estimate of a mean. We remind ourselves that we're interested in a 98% confidence interval, so we change that to 98. And we're given our interval first as a point estimate, namely the sample mean plus or minus the error, and then the lower limit and the upper limit. So let's take this back to our workbook and state the confidence interval. The next thing we're going to do is say this in words. There is a 98% chance that the true population mean for the average intelligence, or I should say IQ, of famous people is between 128.8 and 162.0. Now, we know the units here. We know what this is talking about. We can say this nicely. The average IQ of famous people is between 128.8 and 162.0, which is a nice end to our first example looking at a confidence interval for population means. Okay, our last example of a confidence interval for population means. So example 10, the data in table 8.3.3, you can find it in your book, are the life expectancies for men in European countries in 2011. And that's where the data came from, the World Health Organization. Find the 99% confidence interval for the mean life expectancy of men in Europe. So the first thing is our random variable. So X is the life expectancy of a European male, and mu is the population parameter. So in this case, the mean life expectancy of all European men. So the first thing we need to check is that this is, in fact, a simple random sample. It's pretty close to the number of European countries, so I'm going to guess that it's all of the countries that they have data for in Europe. So I'm going to say that the requirement for a simple random sample is satisfied because perhaps this is a census. That is, perhaps it covers everyone. And then we notice that that's a lot of data points. N equals 53, which is bigger than 30. So we can say, just because of that being bigger than 30, that the random variable is normally distributed. So let's compute the confidence interval inside of a GeoGebra spreadsheet. So I've pasted in the data. I'll select that first column and do one variable analysis. I'll then open the t estimate of a mean, and we remind ourselves that we want a confidence level of 99%, and we get our interval as the point estimate plus or minus the error, and also the lower limit and the upper limit. We can say in the statistical interpretation that interval 71.6 to 75.8 contains the true population mean, the average life expectancy of men in Europe with a 99% confidence. But this is an excellent example and a great place to end Chapter 8 because we can say this really clearly, like something you'd read in a magazine or a newspaper. We can say that the average, that's the way that you'd say mean to most folks, lifespan or life expectancy of European men is between, we've got units here, 71.6 and 75.8 years. And make sure you get that years in there as well. Okay, everyone, thanks. That wraps up Chapter 8.